Hello, welcome. I'm Yuki. Welcome to our second episode of our stream processing. Let's get started right away. In this episode, we will mainly discuss the selection of streaming processing technology solutions. Without further ado, let's dive into the topic. First of all, in our scenario, we will use data fusion, which is similar to Spark SQL. It's a batch processing engine in terms of content type. Currently, we aim to build a stream processing engine on top of it. Well, in the open source world, there are two popular stream processing engines. One is Spark's structured streaming, and the other is Flink. We have drawn inspiration from both of them. However, structured streaming essentially reuses Spark SQL's batch processing engine. So it's somewhat similar to our current requirements and use cases. So it's more relevant. In this section, we'll mainly discuss structured streaming. Why do we decide to build our stream processing engine based on it? Let's talk about its implementation. Some key features of structured streaming processing are that it's an incremental query and model. It has some characteristics. Primarily, it's designed for near real-time processing. Although it also supports real-time processing like Flink. However, the real-time mode is still experimental at this point. So for now, we are focusing on its micro-batch mode, which is akin to near real-time. For example, its incremental query model essentially reuses Spark SQL's batch processing engine. And the reason is that Spark SQL has been around for many years, and it has a series of optimizations. So, building a streaming processing engine on top of it not only covers batch processing, but also stream processing. And many optimizations can be reused. It offers two processing modes, near real-time and real-time. Let's focus on near real-time for now. Structured streaming's characteristics include it cuts the stream into small batches, so it processes data in small increments at fixed intervals. This is why it's called VP mode. It doesn't provide real-time processing like Flink. Let's skip the real-time mode for now. The next slide provides an overview of this VP mode. The VP mode in near real-time processing introduces a certain processing delay. If you look at the timeline on top, it shows the actual time events occur. And the solid line below represents where our processing engine handles the data. The VP mode triggers processing at fixed intervals, as indicated by the purple dashed line. In this VP processing mode, because of these fixed intervals, as shown by the purple dashed lines, the first time it triggers, it processes the 3 data points before it. And the second time indicated by the second purple dashed line, it processes the 4 data points before it. You can see that, for example, the blue data point. Its actual arrival time is quite early, but there's a significant processing delay before it's actually handled. Now, let's take a look at the real-time processing mode. In the real-time mode, the processing delay is much smaller. As soon as a data point arrives, it's processed immediately. So, the real-time mode has very low latency, but it might require more substantial modifications to the processing engine, which may not be necessary for our current scenario. We don't need such substantial changes, because for our use cases, the VP mode completely meets our requirement. Moreover, this VP mode entails relatively small changes, both in terms of the scenarios requirement and cost. So, VP mode is our preferred choice. We'll briefly explain why we choose the structured streaming VP mode. Next, we'll provide a basic overview of some key concepts in structured streaming. First, we'll look at the input and output, which are crucial in stream processing. In structured streaming, which is a stream processing framework, input data and processing it, as well as outputting result, are vital steps. Structured streaming natively supports many connectors, meaning it can connect to the various data sources. However, in stream processing, you may be familiar with different semantics, such as exactly once or at least once processing. To ensure this semantics, certain conditions must be met. For example, the data source must be replayable, like Kafka, where you can specify offset to read from. This allows you to continue processing from where you left off if your program crashes and the system goes down. It avoids reprocessing the entire data from the beginning, which would waste resources and increase cost. Additionally, output requirements include idempotent writing. Idempotent writing means that if you output the same data multiplied, the result should remain the same, rather than appending the data repeatedly. For instance, if you repeatedly output duplicate data, the result should not change, it remains the same. This is what we mean by idempotent writing. Furthermore, some specific things in structured streaming implement exactly once writing to ensure the desired semantics. For our CnosDB, it inherently supports this because it's a time series database. In a time series database, data within the same series and timestamp is deduplicated, which aligns with the idempotent writing requirement. Additionally, structured streaming's API is entirely consistent with SparkSQL's batch processing API. This means that users only need to learn one set of APIs, allowing them to work with both batch and streaming processing. Moreover, structured streaming supports various output modes, such as append, update, and complete. We'll dive into the differences between this mode later. This mode determines which data should be output and when. Additionally, there are some unique APIs like triggers, which are essentially because structured streaming operates in periodic intervals. A trigger initiates the execution of your queries, and the watermarks are crucial in stream processing. They decide when immediately state data should be cleaned up and which delayed data or data that arrived too late should still be allowed for processing. We'll discuss this concept in more details later. I won't go into further detail for now. Now, let's move on to the execution. It essentially reuses the batch processing engine. Because it's relatively straightforward to adapt it for the VP mode. Another aspect to consider is fault tolerance. Because stream processing tasks run continuously, it's possible that a machine may crash during execution. We need to ensure that when the machine recovers and the program is restarted, it can resume processing from where it left off before the crash. This requires mechanisms such as WL, write-ahead logging, or checkpointing to maintain fault tolerance. We have provided a brief overview of these topics. Next, let's take a look at the high-level design of the stream processing model. Since SQL engines typically deal with tables, stream data sources can also be considered as tables, but with continuously arriving data, like an unbounded table. Over time, the number of records in this table keeps increasing. You can think of it as an infinite table, with record continuously being appended. Let's move on to the next section. This is a relatively simple processing flow, demonstrating how it works with streams. I've taken this diagram directly from the official Spark website. It's better to use their diagrams now. They are quite good. Here you can see a timeline with 10 ones, 10 twos, and 10 threes. When we have 10 ones, a batch of data arrives. At this point, our batch processing, which runs periodically, handles this batch of data and store it in a result. You can think of this result as an immediate state for now. Later, I'll explain it in more detail. When we have 10 twos, another batch of data arrives, and the processing result is again saved as an immediate state. Then, when we have 10 threes, our repeat processing engine handles this data and saves it in this state. The output represents our decision regarding which data from this immediate state needs to be outputted to the downstream sink, and at what point in time this data should be outputted. This relates to the output mode I mentioned earlier. We'll dive deeper into this in subsequent discussions. So what we have here is a fundamental flow. Similar to this process, data continuously arrives from the source, and our processing periodically handles it. After processing, it enters an immediately state, and generating output requires certain strategies for selection and decision making. In essence, it's a relatively straightforward model, but there are many details within it, which we'll discuss in more depth later. You can see that this model is quite straightforward. Thank you, everyone. As you all know that our CnosDB Cloud beta is alive now. Welcome to join our Discord channel below, and you can explore more. I'll see you. Bye-bye.